Space-based solar power is the process of using satellites that are equipped with solar panels to collect solar radiation and send it back to Earth wirelessly through either a laser beam or microwave. Due to the solar panels being in space, the traditional issues of power generation being dependent on solar availability and atmospheric conditions are much lower and more energy can be generated. Laser transmission works through a group of small satellites about 400 kilometers above the Earth. The transmission method is a laser beam of about 2 meters in diameter. Each satellite produces 1 to 10 megawatts of power, weighs less than 10 tons, self-assembles, and can be launched in one rocket. The laser beams will be interrupted with the presence of heavy clouds and rain and hold the possibility of becoming weaponized. Microwave transmission consists of one big satellite that generates over 1 gigawatt of power. It is composed of large mirrors on both sides of the satellite that reflect sunlight into the center to be transformed into microwave energy. Microwave beams provide power to Earth without atmospheric interruptions with intensities that are equal to or less than midday sun. To deploy the satellite, it would take many launches. Through net present value analysis, or NPV, it was found that terrestrial solar panels have a negative NPV while space solar power has a high positive NPV. This shows that space-based solar power has a higher value over its lifetime than terrestrial alternatives. Space-based solar power also costs much less than terrestrial solar power based on their cost per unit production. To put this in perspective of another common energy source, we will now compare space-based solar power to natural gas, which produced 32% of the world's energy supply in 2019. A combined cycle natural gas plant has an NPV of $2,000 per kilowatt and a cost per unit production of $0.4 per kilowatt hour. These values show that space-based solar power would be competitive to natural gas. The solar irradiance of space and terrestrial solar power were compared on the basis of a solar radiation of 1,366 watts per meter squared. Space-based would supply 7.6% of the original energy to the grid, much higher than terrestrial's 1.7%. This difference is caused by the lack of atmospheric interference, which allows space technology to produce more energy. To avoid weaponization of laser technology, there need to be limitations on the direction that the system would be allowed to transmit its power. Technology advancements in space travel would also be needed to resolve the challenge of repair to microwave technology. These resolutions could lower energy transmission and raise prices. When compared using estimated CO2 mitigation costs, it was found that microwave transmission would have a $77 per ton CO2 cost, while laser transmission had negative $85 per ton CO2 cost in comparison to natural gas. This difference shows that the cost for deploying microwave technology would have a hefty price tag attached to the amount of CO2 it would prevent emissions of, while laser technology would save money. The largest environmental impact will likely be from the large amount of launching vehicles needed for the deployment of space-based solar power. Today's launch vehicles are very expensive and contribute to atmospheric pollution. This high expense and pollution could cause some opposition from investors and surrounding communities.